Today we're looking at the following problem involving repeated eigenvalues with one eigenvector with systems of linear equations. So you have differential equations, to be more specific. So you've got x prime of t equals, I'm going to read this rows and then columns. So straight across for the first row 3 minus 1, and then my second row is 1 1, and yeah, it's a 2 by 2 matrix times x of t. So we're trying to solve the system of equations, and the first thing we're going to do when you're trying to solve a system of linear, well, there's a few ways of solving these, but one way I'm concentrating here on is by using eigenvalues and eigenvectors. To define eigenvalues, you're going to take the coefficient matrix 3 minus 1 1 1, and you're going to go ahead and just find the eigenvalues. And these are the calculations that I made, and you get lambda equals 2. Now, we're going to get now the eigenvector when you put lambda equals 2 in. So when you put in lambda equals 2 into the system of equations, which is the a minus delta I equals 0. So yeah, if you haven't reviewed eigenvectors or forgot them, I highly suggest you go and review that, just because this whole topic is going to be centered around eigenvectors. So we go ahead and find the eigenvector by putting it into a minus delta I, row reducing, and you get x1 equals x2 here. Okay, x1 and x2 were the solutions to the homogeneous equation here. And yeah, the eigenvector would be v1 equals x1 x1, or just taking the x1 1 1 here. And yeah, you only have one eigenvector. So the problem is, if I only have one eigenvector, I need another one here. So that's what's happening. So that's the issue really today, is you have just one eigenvalue and one eigenvector. So you need to find the rest. And how do I get to this? So I'm not going to get into the specifics. The purpose of this video is just to know how you can do such a thing here. And it's by looking at the following. If A is a 2 by 2 system, A minus delta I times vector V1 equals 0, and A minus delta I V2 equals V1. We have this 2 by 2 system of equations here. We're solving for V1 and V2, essentially. Now, you already solved for V1 from the first equation. That's why I wrote V1 is the associated eigenvector from lambda. So that's not the big deal. The big deal for you is to solve this part over here. So what you're going to be looking for is A minus delta I times some vector V2 equals the vector V1 that you just found. And I know that sounds complicated, but it's not that bad. I'll just get into it in a second. And your solutions for your equation are these two right here. X1 is just V1 e to the lambda t. So how you would usually form your solution of a differential equation if you had maybe multiple eigenvalues and eigenvectors. Now the second solution is equal to V1 times t plus V2, all of that times e to the lambda t. And of course you have your general solution, which would be x equals c1 times x1 of t plus c2 times x2 of t. All right, so let's get to finding our V2 here. And essentially what you're going to do is you're going to plug in your eigenvalue back into your equation, the a minus lambda I. So you get 1, negative 1, 1, negative 1. And what you're going to have is this system right here, a minus 2I, all of that times V2 equals to V1, where V2 equals xy, and you get 1, negative 1, 1, negative 1 times some vector xy equals 1, 1. And essentially what we're going to do is we're going to row reduce again, and you would get this right here, x minus y equals 1, or x equals y plus 1 if you prefer. And if you replaced the x with the y plus 1, you're basically you have an infinite solutions of the form y plus 1 and y. And if you let y equals 1, you come up with 2, 1. You can let y equal anything here. So you would have your solution x1 and then x2 based on what I had said earlier on the top. So basically this is the v1t part plus a v2 times e to the lambda t. Okay, that's what that's all about. And this one on the top is just v1 times e to the lambda t. So those would be your solutions for a 2 by 2. And yeah, here I'm just plugging stuff in. Now, the question you might have is what happens if you have a 3 by 3 or a 4 by 4? So if you have a 3 by 3, purpose of this is not really to go over all the math, but you would do something similar. You would, in this case, I have just lambda equals -1 as one of my eigenvalues. That's it. It's just one. And then I only have one eigenvector again. And this time you'd have to work with this system of 3 equations. So a minus lambda I v1 equals 0, a minus lambda I times v2 equals v1. So it's like what you just did in a sense. But then you have this other one, which is a minus lambda I v3 equals v2. And again, v1 is the eigenvector that you found. And this is what your solutions would look like. x1 equals v1 e lambda t. x2 equals v1t plus v2 e to the lambda t. So I'm just repeating what I just had gone over with the 2 by 2 system. And the x3 of t equals 1/2 v1t squared plus v2t plus v3 e to the lambda t. So essentially, x3 is built up in a similar manner to what you did before with x2, but it's to 1 degree. And the half is there just because it kind of works out nicely. And in fact, that's why we pick x2 as is, because it kind of works out nicely. Well, anyways, that form works out nicely to derive those equations that we're working with the a minus lambda I. Well, anyways, so in our case, we would replace, lambda with -1 and solve, and this is what you get for v2. And then, again, I would replace my lambda with -1 times v3 equal to v2. So you would set up a matrix, and this is what you wind up with right here. So x1 equals 0, 1, 0 e to the minus t, x2 equals 0, 1, 0 t plus -2, 0, 1 e to the minus t, and then 1/2 0, 1, 0 t squared plus -2, 0, 1 t plus -1, 0, 1 e to the minus t is what you get. So it's basically solving these equations for eigenvectors, okay? And yeah, and then this is my final answer here, okay? So that's basically how you would do this. If this was a 4 by 4, then it works out in a similar manner, and in the sense I would have like 1/2 times 3 is like 3 factorial, okay? And a couple other things that I'm not gonna get into that, but you would basically expand about what you have for x3. You have x4 times another type polynomial, okay? So that's how that would look like. But for the 2 by 2 and the 3 by 3 case, you should be good. Okay, well, thank you for your time. Hope this helps.